So the learning outcomes for this class is to be able to write the velocity and acceleration when the reference frame is moving. I'll motivate this with an example and by connecting it to 16.5 and 16.7 where we talked about the velocity and acceleration formula. So assume there's a disk which is spinning with an angular speed omega and angular acceleration alpha. So we written down that VB is VA plus omega crossed RB with respect to A, and we also wrote down AB is AA plus alpha crossed RB with respect to A plus omega cross RB with respect to A. So this is what came out from 16.5 and this came out from 16.7. Now this expression is true only if B is fixed or it is not moving. Like for example, if there's a point on the tire and it is not moving, then this expression is totally true. However, consider this situation. This is a tire and this is not a point, but it is, let's say, an ant which is moving on the tire. Moving, okay, with velocity and acceleration with respect to disk. Okay, so this is same point B, point A. However, this point B is, let's say, an ant. It's moving with respect to the disk. In this case, VB and AB formula described earlier here are not valid. Okay. And this happens because B has motion, and that motion is in a frame which is the disk, and that frame changes with time. So in this case, it turns out that in this case, the formulas for velocity and acceleration are given by the following. So before I do that, let me just draw a general body BA, and this is moving with an angular speed omega. This is the big omega. So the velocity of B is given by velocity of A plus the big omega crossed with RB with respect to A plus velocity of B with respect to A in frame XYZ. So if you look at this formula closely, the only thing I added to this formula is the third term. Okay, that third term gives me the relative motion of B with respect to A in frame XYZ. So this is frame XYZ. So this is also known as the three-part velocity formula. Similarly, the acceleration can be written as acceleration of A plus big omega dot, or the angular acceleration crossed with RB with respect to A plus omega cross RB with respect to A plus, we'll continue on the next line, 2 omega crossed VB with respect to A XYZ plus A B with respect to A XYZ. So this is the formula for the acceleration, It is called the 5-term acceleration, 5-term or 5-part acceleration formula. It has these two terms which don't appear in the earlier formulas. This term, first term, the fourth term, this term is known as the Coriolis acceleration. Okay, and it only occurs because the point P has motion relative to the frame, and this A B with respect to A is the motion of B with respect to A in frame XYZ. So in our back to our ant example, if this point B, the ant has some velocity with respect to this frame, then that is VBA, and if it has an acceleration with respect to frame A, that's AB with respect to A XYZ. So let's try to use what we have learned into and solve a problem. Okay, so block A is attached to a cord. This is block A. It is attached to a cord and moves along a slot on a horizontal forked rod. This thing. At the instant shown, the cord is pulled down through the hole O with an acceleration of 4 meters per second squared. So you're given that AA with respect to O is 4 and velocity of 2. So VA with respect to O is 2. Determine the acceleration of the block at this instant. You're told to find the acceleration of the block and the velocity of the block. And you're also given that the rod rotates with a constant angular speed of 4 radians per second. Okay. Now, the reason why this particular problem fits in the bill of moving reference frame is because point A, which is what we have asked, is not only moving in the slot with its own velocity, it is also rotating because the fork is rotating. So this is where we have to use the 3-point velocity formula. So velocity of A is velocity of O plus the big omega cross R A with respect to O plus VA with respect to O with respect to X, Y, Z. Now we can write VO equal to 0. The big omega is the angular speed of the fork, that's 4k, and the vector from 0 or O to A is along the x-axis. It has a magnitude of 100 mm, so 0.1 meters, so 0.1 times I, plus velocity of A with respect to O is 2 meters per second, but it's pointing in the negative x direction, so it's minus 2I. So when you do this math, velocity of A comes out to be minus 0.4 J minus 2I. Okay, let's try to see how to use the acceleration formula. Acceleration of A is acceleration of O plus big omega dot with RA with respect to O plus big omega cross RA with respect to O plus 2 big omega crossed with RA with respect to O. Sorry, this should be VA with respect to O in frame X, Y, Z plus AA with respect to O in frame X, Y, Z. So the acceleration of O is 0. Since this fork rod is rotating with constant speed, big omega dot is 0. So the third term is big omega, which is 4k times 4k crossed with the vector from 0 to A. That's, we found that to be 0.1 along I plus 2 times 4k crossed with VA with respect to O is 2 along the negative I plus AA with respect to O is 4 again in the negative I direction. So once you simplify all this, what you get is AA is equal to minus 5.6 I minus 16J. Okay. Okay, so let me just tell you a bit more about this, which might make it more clear as to what is really going on. Okay, so summarize. This slot allows A to move along the x-axis, but because the fork is rotating with an angular speed omega, it also spins. So when you try to look at the motion of A with respect to O or 0, that is basically the velocity of A with respect to O. So an observer at O would notice that A moves with the velocity of 2 meters per second towards him or towards the negative y-axis. Okay. However, an observer here, when he looks at this particular system and he specifically looking at the motion of or the velocity of A, he sees that A not only moves towards O, which is this, he also notices that A spins about O. Okay, the velocity with which it spins about O is given by this component. So this observer sees that A moving like this as well as moving in the negative j direction. So it's moving like this. Okay. So that is how you can interpret this formula. Similarly, the acceleration, this part gives the acceleration of A as observed by an observer at O. Okay, and this acceleration here is the acceleration observed by somebody who is outside this fork rod. He notices A has not only centripetal acceleration, which is this term, it also has relative motion to O, as well as this third term, which is the Coriolis acceleration. That's it. Okay, let's solve another problem. Okay, let's read it. At the instance shown, rod AB, so AB has an angular speed of 4 radians per second and 2 radians per second square. Okay, determine the angular velocity and angular acceleration of the rod CD at this instant. Okay, so since we are told to find that, I'm just going to assume it's in the counterclockwise direction. Omega CD and alpha CD are unknowns. We are also told that the collar at C is pinned and connected to CD. It moves freely along AB, so it slides freely along AB. Now, in this problem, the point which has Coriolis terms and which has motion with a motion which is changing in terms of the direction of the frame is point C, because C is going to slide back and forth, but it's also going to rotate because it's on AB, which rotates with time. So what we'll do is we'll try to write the velocity of C, okay, by looking at it in terms of CD. So velocity of C is velocity of t plus omega CD cross with C with respect to t. Okay, and the reason why this formula will not have the Coriolis term is because when you look at C on CD, that point C is only going to move in an arc. It's not going to have relative motion. So VD is 0, omega CD is unknown, so I'll write it omega CDK, and the vector from D to C, I need to write a vector from D to C, but in order to write that, I will create a coordinate frame like this. So CD, or the vector from D to C, is 0.5 along negative I. Okay. Now in this equation, I have an unknown omega CD, but I also don't know what VC is in order to be able to solve for omega CD. So I need to find another way in which I can find velocity of C. Now what I'm going to do is I'm going to try to write the velocity of C in terms of A. So velocity of C is velocity of A plus big omega crossed with our C with respect to A plus velocity of C with respect to A in frame X, Y, Z. So the reason why I wrote the three-term acceleration is C not only has motion back and forth along the rod, it also rotates about AB. So velocity of A is 0. This is simply the angular velocity of AB, that is 4k, times the vector from A to C. This is the vector from A to C. So in order to do that, what I do is I notice that it is given by 0.75 is the length times the unit vector in this direction. So I can decompose that into this component and that component, and the component along the X or the I direction is simply sine of 60 degrees and the J component is pointing in the negative J direction, so it's going to be negative cosine 60 degrees J. Okay, so that completes the second part. Now the third part is velocity of C with respect to A. This is the motion of C as observed by a person sitting at A. Now I do not know that velocity, however I do know that velocity of C with respect to A is going to be along the slot. So I'm going to assume that I don't know the magnitude, I know the direction, which is this, same as this direction, so it's sine 60 degrees I minus cosine 60 degrees J. So when I try to now take 1 and 2 and equate them, because both of them gives me the velocity of C, right? So I get omega CDK cross 0.5 times minus I equals 4k crossed with 0.7 sine 60 degrees minus cosine sine 60 degrees I minus cosine 60 degrees J plus VC with respect to A sine 60 degrees I minus cosine 60 degrees J. Okay, so when I equate, so this is really two equations because there's an I and there's a J component. So I can compare the two sides for I and J. We have 0.5 omega CD is equal to 2.6 minus 0.5 VC with respect to A, X, Y, Z. And the second part is 0 equals 1.5 plus 0.866 VC with respect to A, X, Y, Z. So just from the second, so two equations, two unknowns. So just from the second equation, we can solve for VC with respect to A in frame X, Y, Z. It turns out to be minus 1.732 meters per second. And by putting that value in the first equation, we can solve for omega ct. It comes out to be minus 6.932 meters per second. So we've got the angular speed of CD. Okay, so having done that, let's move on to find the acceleration. Okay, again, we can write the acceleration of C in terms of acceleration of D. It's going to be minus omega squared CD crossed with RD with respect to C plus alpha CD crossed with RCD with respect to C. So this should be C with respect to D. Okay, so that's the formula. Now acceleration of D is 0. And again, we do the same 3-point acceleration formula because C doesn't quite have, it doesn't slide along CD, it slides along AB. Okay, omega CD is known, it's 6.932 square. The vector from D to C is 0.5i along negative I, plus alpha CD is an unknown, so alpha CDK cross the vector from D to C is again minus 0.5i. So I've got AC, a formula for AC. The single unknown is alpha CD. So what I'll try to do is I'll try to write another expression for AC. Okay, this will be based on looking at C from A. So AC is AA minus big omega, plus big omega dot with RC with respect to A plus omega cross R C with respect to A plus 2 omega cross VC with respect to A in frame XYZ plus acceleration of C with respect to A in frame XYZ. Okay, now acceleration of A is 0. Big omega dot is simply the acceleration of AB, that is 2k. The vector from A to C, I had written it down earlier, it's 0.75 times unit vector in this direction, so that is going to be 0.75 sine 60 degrees minus sine 60 degrees I minus cosine 60 degrees J plus omega cross RC with respect to A. Now this can be simplified easily. So omega cross RC with respect to A is given by minus omega square RC with respect to A. So that is going to be, I'm going to write this as 2 square, because big omega is simply omega AB. Looks like I did a mistake. This should be, oh sorry, I'm good. Omega CD is basic omega, big omega is AB, omega AB. So I'm going to write this as 4. So it's going to be 4 square times the vector from A to C is again 0.75 sine 60 degrees I minus cosine 60 degrees J. Okay, what I did here was I used the fact that this is omega, big omega square R C with respect to A. Okay, and then there is this term which is 2 times 4k crossed with the velocity of A with respect to C, which I already found out. It is minus 1.732 in the direction of sine 60 degrees I minus cosine 60 degrees J. And the final term which I'm left is AC with respect to A, and unfortunately I don't know it, so I'm going to write it as AC with respect to A. This is the magnitude, and the direction is going to be the same as velocity, so sine 60 degrees I minus cosine 60 degrees J. This is equation 4. Okay, so now I have two equations. There's one equation in for AC 3, and it has an unknown alpha CD. There's another equation for AC, and that has, you can see it right here. This is the expression, this whole thing. It has the only unknown is AC with respect to A. So what I'm going to do is equate 3 to 4, 3 to 4, and compare I and J. So if you do that, do the math, turns out that what you get is 16.54 plus 0.866 AC with respect to XYZ equals 24, and minus 4.7 plus, sorry, minus 0.7 minus 0.5 AC with respect to A. So this should be C with respect to AXYZ, C with respect to AXYZ equals minus 0.5 alpha CD. So two equations and two unknowns, so you can solve for them. So it turns out that if you solve them, you get AC with respect to A with frame XYZ equal to 46.81 meters per second square, and alpha CD is 56.21 meters per second square. So we were after alpha CD, and so this is the value of alpha CD. Okay, so let's just summarize what we did. So in this question, we were asked to find the angular speed of omega CD and alpha CD. In order to get the speed and angular acceleration, we tried to find the expression for C in two ways. We looked at C from D. That velocity formula and acceleration formula we've done in 16.5 and 16.7. That velocity was a function of omega CD, and acceleration was a function of alpha CD, which were unknowns. In order to solve for this, then we try to find an expression for C in terms of A, and that was a 5-point acceleration formula and 3-term velocity formula, because C has motion along the slot as well as it rotates as AB rotates. So it's under a moving reference frame. So when we wrote that formula down, we had to write it in terms of velocity of C with respect to A in frame XYZ on this frame, and acceleration of C with respect to A in frame XYZ. So when we took that formula for velocity and equated it to the velocity which we obtained earlier, we were able to find omega CD as well as the velocity of C. Similarly, when we tried to use the acceleration of C, looked in two ways, we were able to find alpha CD and the acceleration of C in this frame. So this is how you go about solving problems involving the 5-point acceleration formula.